The world's revelation has been quietly waiting to unfold in space, where light travels billions of years, a revelation that may rethink our understanding of everything we thought we knew. When NASA launched the ambitious James Webb Space Telescope, JWST project, this is the story of the telescope, an early instrument of discovery, and the deep secrets it began to uncover. The shock waves it would send through the scientific community and question the universe's very foundations were unanticipated. However, a new phase of space exploration has begun with the first images sent back to Earth. This phase will force us to reevaluate the origins of galaxies, the physics that governs them, and even the beginning of the universe. The James Webb Space Telescope provides us with a brand new perspective on the cosmos with each image it takes. One of the greatest feats of human engineering, our investigation of the universe now enters a brand new and exciting phase. The darkest reaches of the universe are said to be unexplored by this telescope. However, the more we investigate, the more obscure it becomes. In fact, with the James Webb Space Telescope, JWST, around, the deeper you look, the less you see, might become the new planetary motto. The beginning of a new era in space exploration can be traced back to JWST's launch. The world now has a first look at all of this highly anticipated device's capabilities. A mission that has been in the works for more than 2 decades. With a cost of $10 billion, NASA's JWST is the most expensive science probe ever built. Its goal is to take pictures of stars from the first galaxies that formed in the blaze that followed the Big Bang. The Webb telescope finally returned images that shocked the scientific community, despite numerous delays. These images suggest that we may need to rewrite the books on how the universe began and challenge our understanding of the nature of galaxies. Around 14 billion years ago, the Big Bang signaled the beginning of consciousness throughout the universe. The physical laws that we know today did not apply at that time. Elementary particles like electrons and photons, as well as neutrons and protons, the atom's building blocks, exploded into matter in a matter of seconds. Over vast stretches of time and space, the primordial seeds of stars, planets, and galaxies spread out. The universe became extremely flat on a large scale as a result of this expansion, indicating that its contents were evenly distributed. However, matter is concentrated in clusters of galaxies and stars on smaller scales, such as between galaxies or within the solar system. According to physicists, something they refer to as inflation took place shortly after the Big Bang. In a matter of seconds, what was once a small, dense universe expanded rapidly and continues to do so today. The lambda cold dark matter (CDM) model, which is the current standard model of the universe, includes inflation as an essential component. The universe's path is depicted in this model as accumulating and expanding over time. In any case, new pictures taken by JWST highlight a different universe at the edge of our comprehension. These images demonstrate that the universe's history is more complex than previously thought. The cosmic microwave background, CMB, a trace of radiation from the beginning of the universe, is one of astronomy's pillars. These waves can be picked up by radio telescopes and turned into heat maps, which show how matter is distributed in the universe 400,000 years after the Big Bang. Understanding the universe's origins and development is made easier by this illustration. We also know that the universe is always changing and that we can measure time in some dimensions. The CMB confirms that the past of the universe was extremely hot, whereas the present is cooler. Examining very distant galaxies, effectively looking back to the first 100 million years after the Big Bang, is one method for evaluating this model. The Hubble Space Telescope was used by astronomers in 1995 to photograph the very first structures in the universe. Hubble took 342 images of a region in Ursa Major over the course of 10 days. Rather earlier than expected, astronomers discovered thousands of galaxies at various distances and stages of development. In 2016, the most distant galaxy ever observed, GNZ 11, which existed 400 million years after the Big Bang, was discovered by astronomers. Despite the fact that it was small and isolated, this faint burst in the night sky did not cast any doubt on the CDM model because it was so early for a galaxy. However, the universe's history was altered when the James Webb Space Telescope arrived. Galaxies formed much earlier after the Big Bang than previously thought, as demonstrated by NASA's $10 billion project. which will be operational by summer 2022. Contrary to existing cosmological assumptions, some of these galaxies are surprisingly massive and awash in stars. These galaxies, which are more than 10 billion times as massive as our Sun, are thought to have formed between 350 and 500 million years after the Big Bang, according to some researchers. One of these universes even gives off an impression of being more monstrous than the smooth way, in spite of our world having billions additional years to frame and develop. We are in uncharted territory if these measurements are accurate, necessitating a fundamental shift in our understanding of galaxy formation or a modification to cosmological models. One extreme possibility is that the universe expanded sooner than anticipated immediately following the Big Bang, necessitating the creation of new forces and particles. Based on our current understanding of models, we should be able to figure out how atom-based gas and matter fall onto these early galaxies and how star formation feeds back and prevents new gas from entering. Normally, 10% of the gas becomes stars. However, in order to form galaxies of this size and speed, nearly 100% of the gas must become stars. Despite the fact that 100% can be achieved, it's possible that the circumstances will be drastically different from what we anticipate. This prompts the inquiry, are all planetary systems incorrect? Should the Big Bang theory be rethought to better explain how the universe started? Many people believe that new physics laws and phenomena, such as the first form of dark energy appearing shortly after the Big Bang or the universe being born with supermassive black holes, may be at play as the scientific community investigates these issues. Others suggest that matter has external properties, like new particles that take a long time to decompose into regular matter over a lifetime. History has demonstrated that even the most absurd assumptions can sometimes be correct, despite the oddity of these ideas. Numerous issues with the CDM model had already surfaced prior to the introduction of JWST. One of the mysteries of modern civilization, for instance, is still the nature of dark matter. Particles that make up dark matter remain elusive despite numerous searches employing various detection techniques, such as direct detection experiments and indirect astronomical observations. The study of dark matter has significant repercussions for our comprehension of galaxy formation and the vast structure of the universe, in addition to providing solutions to fundamental physics questions. The difficulty of refining our models is highlighted by the gap between simulation predictions and observational data on the distribution of dark matter, such as cusp versus core problems. While observations reveal a wide core distribution, particularly in small dwarf galaxies, simulations frequently predict cuspy halos at the center of galaxies. The issue of satellite loss is another one. The number of satellite substructures around massive galaxies like the Milky Way is frequently overestimated by simulations. The interaction between dark matter and baryonic matter, which includes ordinary matter like stars, gas, and dust, is questioned by this discrepancy. To improve our cosmological models, we need to know how baryonic physics affects how dark matter structures form and change. Another significant test comes from estimating the Hubble consistent, which depicts the universe's pace of extension. Different approaches and brand new discoveries have led to contradictory outcomes. When compared to values derived from the global microwave background by missions like the Planck satellite, local measurements reveal that the Hubble constant has a higher value. This concern brings to light the possibility of systematic errors in measurement techniques or errors in our current understanding of global parameters that call for additional research. The conceptual framework of the CDM model faces several questions in addition to these visual issues.